This is the coolest one of the day. It's not lame like Sam's previous talk. All right, so we're good?
We're going.
All right. Hey. Just a quick show of hands. How many people do we have here? Computer science majors or from the computer science? Yeah. All right. You guys are the best. Okay. So my name is Mark Sanders. I'm going to talk about the general topic, a little bit of what's called hash reversal or password recovery. But I'm also going to take the advantage of the fact that I'm here at BloomCon at Bloomsburg University to discuss a new algorithm that we've developed where I work at Nobliss called the Bloom Reverse. It's a happy coincidence it's called that, and you'll understand why it's called that. But it's not because I'm here, but I think it's also kind of convenient and nice. So I work for an organization called Nobliss. We're a nonprofit research and development and consulting company in the Northern Virginia area near Washington, D.C. We have a booth downstairs, and of particular interest to this crowd, we do internships, and they're paid. So you should look us up online, and every year we do. I think we take, what, about 60 interns a year, something like that. It's very competitive. And we even have here Erica, whose last name I can never remember how to say. I call her Macy Juicy, is an alum here from Bloomsburg who started as an intern and now works for us. So it's a great place to work. It's a lot of fun. And also I'd like to point out some of my colleagues who helped on some of this work: Tyler Barris, Mark Walters, Scott Liu, and Sam Gross, who's here, a former professor, and who's helped with some of the optimization and math work on this as well. All right, so who am I? I spent about 17 years supporting the Department of Defense and Intelligence. My education, my undergrad was in computer science, which is why I like you guys. My master's was in management, both from George Mason University in Virginia. I've been various jobs in the past. Right now I'm a manager of a data analytic group at Nobliss, but I've been a computational linguist at one point and program managers for various kinds of fun things for the DoD. Last year I gave a presentation on the Ashley Madison leak, where a lot of people's sad information was leaked all over the internet. What's of particular interest for this talk is the fact that there's a group named Cynosure Prime that was able to, what they called, crack 11 million of the passwords, a little bit more than 11 million of the passwords that were leaked as part of that leak. So what I'm really interested in talking about is how do they do that? What does that mean to crack a password? Last year what I talked about a little bit was some of the implementation flaws that Ashley Madison had in the code of how they actually manage the passwords and user accounts. And it turns out, as we have seen more and more leaks happen on the internet, that it's fairly common practice for organizations to have very poor password management policies, so that when their password information is leaked onto the internet, it's fairly easy to actually figure out what their passwords are. So Wikipedia talks about password cracking in terms of a process of recovering passwords given what's called a password hash or a digest. There's a bunch of different approaches for doing this. The common approach that Wikipedia talks about is brute force, and I'll actually talk a little bit about that. But then there's also what are called algorithmic approaches to trying to reverse these things. So I'm going to start with just some definitions if you're not familiar with this, this topic, just so you can kind of get an idea. And by the end of this talk, this is going to get pretty in-depth, but hopefully you'll be able to follow a lot of this if you're not into this topic directly. But the basic idea is that a hash function is some process where you take a password, say my password will be some password. It's a terrible password, by the way, don't ever use that. But say I have a password, I put it through my hash function, and I end up with what for this talk I'm going to call it digest. Colloquially, a lot of people call them hashes, but really the sort of the formal term is a digest. And it'll maybe look something like this. It's a big long alphanumeric string. Okay. So a hash function is a one-way function. There's a lot of interesting math and theory behind one-way functions, but for purposes of this talk, we'll consider a hash function to be, I'm going to use some notation here, H, and the password to be P, and the digest that's produced by that to be D. And the basic idea is, you can see, for example, I have some what we're going to call keys. We can also think of this as passwords, but they can really be any string of any length, and they will go through some hash function and produce a digest. So in this example here, you see Lisa Smith, after going through the hash function, is the hash or the digest 0, 1. So how do hashes work? Here's probably the worst possible hash that you can ever imagine, but it's a nice simple example. It's actually sort of like the starter hello world hash function that people learn. So for example, if I have a password, my password's password 1, I get the ASCII codes for all the letters, add them up, I have a number, the number's 900. That's my digest. So very, very simple. The question is, if I were to give you 900 and tell you that belongs to some password and not let you know what that password is, could you figure out that it was password 1 with no other knowledge at all? And that's essentially what this topic is about. There's also a concept called cryptographic hashes. So hash functions are used all over computer science for a wide variety of reasons. If you studied hash tables, you probably produce some on your own. There's also other kinds of hashes which are used for various types of database functions and indexing. And they have various different kinds of properties. What we're specifically interested in here are what are called cryptographic hashes. And there's essentially 5 major attributes of a cryptographic hash. So the first one is they're deterministic, which means that if I were to give a cryptographic hash function the same password over and over again, I will get the same digest over and over again. I won't ever get something different or variable. Another one is that they're very quick to compute the digest, but the reverse is very, very difficult or intractable. The number 4 is that if I were to say have password 1 and compute the digest for that, and then compute the digest for something that's password 2, even if I've only changed one letter, the digest will be completely different, and there's no correlation that I can easily determine between the passwords and the digest, even given small changes in the passwords. There's actually an entire class of passwords that try to preserve those small similarities, and that's actually a very interesting topic, but they're not cryptographic hashes. And then the other question here, and this has actually recently been in the news, if you've been kind of looking a little bit at some computer security news, that it's very, very difficult to compute 2 different passwords that will force a collision. And a collision means that they will both produce the same digest. Recently, and I'll talk about this very, very briefly, but recently Google announced the ability to generate collisions in SHA-1, and they showed some examples of 2 different PDFs. They're completely different PDFs, but they compute to the same SHA-1 digest, and that's forcing a collision. So that's kind of an interesting problem. All right, so just some real examples of what are cryptographic hashes. Actually, not all of these are cryptographic hashes, but MD5 is a very common one. It's used all over the place. It's actually now misused. It's a very, very, very broken cryptographic hash. But you can see some examples where if I have MD5 password 123 that produces this long alphanumeric digest, and password 1234 produces something that looks completely different. The key thing, and again, is it doesn't matter what the length of the input string is. I'm talking about passwords today, but it could be the entire text of War and Peace. The digest will be exactly the same length. And that's another sort of property of hash functions and digests. There's entire families of cryptographic hash functions. The SHA one is very widely used. It was the topic of the Google research, and they were designed by the NSA. There's some conspiracy theories that the NSA, specifically weakened the algorithms, but that's just a lot of fun. And there's also ones that you might have also heard of called cyclic redundancy checks, which are often used to help determine that if a file has been tampered with or damaged in some way. And these are all different kinds of use cases that you can use hash functions for. If you attended the talk this morning on Chip Off, they talked about how you can forensically treat files by taking producing a digest of a file, and then when you work with the file, you then produce the digest at the end of the work to verify that you haven't damaged or altered the file in some way. So there's lots of different use cases for hashes. All right, so let's talk a little bit about hashes being one-way functions. And just introduce some more notation. So h of p equals d, that means I'm hashing the password, I'm producing a digest. There's no simple reverse function such that I'm going to introduce a new piece of notation here, r, which means the reverse of the digest guarantees you retrieve the original password. If you think about this is kind of obvious too. Because I'm mapping passwords into digests, there's an infinite number of possible collisions. So given some digests, I can actually produce an infinite number of possible, what we're going to call quote-unquote passwords that map to that digest. So it's actually very, very difficult to do this. Just a little bit more definitions. So we're going to call something the password space. And if you think about sort of a set of rules for what passwords can be, we've all produced passwords for online accounts or here at Bloomsburg. They tell you have to have like a digit, you have to have a special character and uppercase letters. If you look at all those rules and you permute all the possible passwords under those rules, that's called the password space. So a very simple password space here might be 5-digit numeric pins. That produces 100,000 possible passwords. But 5-digit alphanumeric pins produces 60 million possible passwords. So just a slight change in rules can actually drastically increase the password space. And then there's also what's called the digest space. That's all the possible digests given a specific hashing approach. Just to give you an idea, let me go back here. So if you see these digests under MD5, see how long they are. They're actually a hexadecimal, so they can have 16 possible values for each number. And the number of possible digests you can produce under MD5 is extraordinarily huge number. And that's called the digest space. Right? So just a little bit more reiteration on collisions. You see in this example on the right, John Smith and Sandra D, they both hash to the same value, and the term for that is a collision. And what that means is that if you're reversing, given a digest, and you're trying to reproduce the password that produced that digest, it doesn't really matter which one you get. They're both actually the equivalent passwords. So just by coming up with one, basically satisfies the requirements for coming up with any of them. Okay. Here's Google's announcement. This was on February 23rd, announcing a SHA-1 collision. So this is pretty topical, and that's outside of the scope of this talk. It's actually really interesting to look into. I believe it was one of the online Git repositories. Someone actually uploaded both PDFs, knowing that they use SHA-1 as their file deduplication mechanism and crashed the system. So that's a lot of fun involved in that. So just a really simple example of how servers might store this information. When you log into a system and you give it your username and password, that system doesn't actually keep your password. There's lots of different schemes and mechanisms for how they store this information. But generally what they store is your username and the digest of your password. And the theory is that if someone were to break into that system and store the password file, all they would get would be the digests. And that would be very, very difficult for them to then reproduce the passwords. But as we've seen with a lot of these big leaks, like Ashley Madison, that's not the case. It's possible very frequently to recover the passwords. And just a little bit of how digest logins work. This is a very, very simple example. The idea is you may send your username and password to a service. They will hash your password and produce a digest and compare that digest to the one they have in their file, and that will determine whether you're then authorized to use the service or not. Sometimes the hashing happens on your side, sometimes it happens on their side. It just sort of depends on what the scheme is and how they've designed their system. Okay. So just again, there's no easily computable reverse function, R of D equals P. But even though R of D equals P doesn't exist, we can sort of pretend that it does. And if we live in a world of pretend, a lot of things are possible. Right? And so everyone's smart in the land of make-believe. And so let's talk about what this means, right? So here's the simplest idea, right? So we'll simulate R of D equals P using what's called brute forcing. And that basically means we're going to, given a set of rules, we're going to design a password space, and we're just going to simply start trying all the passwords in that space and hash each of those passwords until they produce a digest that is the digest that we desire, right? So here's a little pseudocode, and you can see given some digest, I have a set of P that designs some password space, and I'm just going to try them all. I'm going to hash them and see if it matches the digest, and if it does, I'm going to kick out, and now I know what either the original password was or some equivalent password, and that's the key factor here. And I'm going to do a little live demonstration. So this is on I think it's 8-digit pins. My colleague Tyler Barris wrote this code, and I'm going to brute force that. And this is a worst case example where the pin that I'm trying to recover is all 9s. And I'm going to start at the beginning of the password space, and I'm going to print out an example. And this can give you, I just want to kind of give you an idea, a rough order of magnitude, like what does this look like when I'm doing this, and how long does this take? All right, so it's tried 10 million. It's tried 20 million. There we go, 30 million. So we're about almost 30 million. So we're about a third through the space. This is a very, very small space. And you can't see it, but the code is already provided with the digest that it's trying to hack. Question? This is SHA-512. So this is still, under NIST standards, considered to be a secure hash type, a cryptographic hash. Okay. You can imagine, though, on a much larger password space, this is going to take a lot longer. And most of our passwords are not just pins. They're going to have alphanumerics. They're going to have 11, 12 digits, special characters, all kinds of things. But just real simply, you can see. And this is, by the way, this is running single-threaded. So this is really, really worst-case scenario. Ideally, you'd multi-thread this or use a GPU or something to try to attack this problem. But we're almost done. All right, so on this reasonably modern laptop, single-threaded performance, SHA-512, it takes, here we go, about 90 seconds. That's consistent across multiple runs of this to reverse that, right? So it found the pin, which was all 9s. We're very excited about that. So you can imagine if I had 60 million passwords. Let's say I received the Ashley Madison password list, and I was trying to reverse those, and I was able to get through, say, 11 million of those at 90 seconds a pop. That's quite a long time, right? So this takes a long time. Yeah. Oh, for each file?
Yeah, so you're guessing the password, and then you use the digest of it.
You can, but remember the password space in that kind of example is going to be much bigger than this. So yeah. You can check it against all of that, and that would be a speed up. I'm going to go actually through some ideas about how you can speed this up, but that would be an example. There's different ways you can parallelize the problem. That would be an idea, right? But the basic premise is we want to make the password space smaller. And the truth of it is we don't all just use a list, a string of random characters for our passwords. We have something that we have to remember. Or if we're a terrible person like I am, you probably write it down somewhere, or take a picture of it and put it on your phone, as we heard this morning. That's really also a terrible idea. But there's all kinds of strategies for this, right? So a real simple one is do what's called a dictionary model, where you have a list of, say, English words, and then I'm going to actually have a little example here. All right. And then you have some rule about how you permute each dictionary word so you can produce some variants of that word. And then you just sort of use those as the inputs, right? So you're shrinking the space down to something more manageable that takes less time to compute. There's other ones, too, that look at like typability modeling, right? So you don't want a password that's really hard to type. So now you have to be able to remember it, and you have to be able to type it easily. Or you could look at profiles of human memory, like how long can a password be, and what complexity can the passwords have so the average person can still remember it. There's all kinds of rules around this and ideas about this approach. But the basic idea is, let's cheat a little. Let's get rid of most of the passwords that we don't think that people could ever use. Some other ideas to make it faster, right? So instead of starting at the beginning of the password space and trying every single one, because in this case, you saw sort of a worst case example where the password was actually at the end of the space, I could just randomly sample it across the space and hope that speeds it up. And that can actually be a performance improvement, believe it or not. But you also want to keep track of what you tried in the past, so you don't just keep trying the same thing. And you want good entropy sources so that as you randomly sample, you don't get stuck in non-productive clusters where the password is maybe over here. You can parallelize, right? You can use GPUs. That's sort of the hot topic right now. Here's my little animation, the best I can do in PowerPoint, right? So I found the password. One of the problems is that not all of the hash algorithms have a GPU implementation, and quite frequently, the way that passwords are hashed is that they'll salt the password space, or they'll modify the algorithm slightly or wrap it within another approach, and getting that to work on a GPU can be very, very challenging. So these approaches actually, this is sort of what the state of the art is. You can go on the internet today and you can download these tools, John the Ripper, Hashcat, Dave Grohl, and they use different strategies and different approaches for trying to reverse passwords. A lot of them do have some pretty cool GPU implementations for a lot of the hash algorithms. I think Hashcat actually has a very sophisticated dictionary-based approach, which can actually really speed things up quite a bit. But it still takes time. It takes a lot of time to crack each password. So what's another approach, right? So we've talked about how we can muscle our way through doing this. So there's a wonderful researcher, Martin Hellman. If you have studied cryptography at all, you'll be familiar with something called the Diffie-Hellman exchange. It's the same Hellman, not the Hellman mayonnaise guy. That's a different guy. It's confusing. I get confused about it all the time because I'm always thinking about food. But he also is known for coming up with an approach called rainbow tables. And if you've ever heard of rainbow tables on the internet, I'm going to actually go through a little bit of an explanation of what they are because they're really cool. It's actually a really elegant and cool way of having a nice time-space trade-off for reversing passwords. They have some downsides, but they're pretty interesting, right? So just kind of a few more definitions to help explain what a rainbow table is. So we've talked about what a hash function is. So you can see here I have a slight change in the notation, right? So I have h of p sub n equals d sub n, right? So assume that I have some ordering to the password digest pairs. And then his key contribution is coming up with what's called a reduction function. And what that does is that maps digest back into the password space. It's not a reversal. It's just some rule set that says if I have some digest and I run it through this function, I will produce something which is valid against the rules of the password space. Okay? So you can kind of think of maybe like an inverse of a hash function, not a reverse. And what's cool about this is if you use them in sequence, you can produce what's called a hash chain. So you can see here I have h of p sub n equals d sub n. Then the reverse of d sub n equals p sub n plus 1. So I kind of move forward in this chain. And then I take the hash of that, and then I take the reduction of that, and so on and so forth, right? And what a rainbow table is simply a set of hash chains. Okay. So you can see here, I'm calling here at the top a hash chain C. I'm going to call it C sub 1, right? Which is the set of where the list of passwords and digests in the sequence that they would be produced if you were to alternate between hashing and reducing. Okay. I just didn't talk here about the algorithm. I think it's a lot more interesting if you can just sort of see it. I have an example I can show you. But the key contribution here and why this is important is that since you know what this password was at the start of a chain, and then you alternate through some number of the hashes and the reduction functions, you'll know what the last digest was that was produced, which means you can throw away all the junk in the middle. And all you have to do is store the first password in the last digest, and you can reproduce fairly trivially all the stuff that was in the middle of that. And that saves an enormous amount of space. So you can imagine if I have a hash chain that goes on for millions of terms, I can either store the million of those terms, or I can just store the first and last of that and easily recompute what's in the middle. Okay? So it's better than brute force in the sense that I only need to work within a single chain rather than having to try things across the entire password space. And if you really think about this, you kind of squint a little bit, this is really a very novel way of reducing the password space so that we're looking at the space that only belongs in a chain. It's just a little harder to describe without doing it this way. What's cool is that, and another part of this is that someone has to pre-compute the rainbow table to start with, right? Somebody has to compute from the first password to the last digest, and they have to store all the stuff somewhere. That takes a long time to do. Turns out this is such a common approach. You can just go online and buy sets of rainbow tables. I forgot what site I got this on, but it's pretty easy to look up. For $2,700, available by PayPal, they'll ship you a 6 terabyte hard drive with rainbow tables for MD5 and SHA-1 and what is it, NTLM, which is I think the hash function NT uses. It's not terribly expensive compared to the compute resources necessary to build this in the first place. And so here's just a quick example of how a rainbow table might work. So I'm going to have a rainbow table of 2 chains. It's fairly trivial. Chain 1 starts with password 1 and digest 3. Chain 2 starts with password 4 and digest 4. Okay. So I have a digest I want to reverse, digest 2. Is digest 2 in the rainbow table? So I'm going to compare it to C1, and that means I'm going to look at the last digest in C1. And no, it's not in there. D2 does not equal D3. What about, is it in the second chain? No, D2 is not D4. So all I have to do is reduce D2, produce another password, hash that. I'm going to get D3, try again. When I do that, I find that, yeah, D3 is in the first chain. That means now I know, I have some knowledge that D2 is somewhere in the first chain. All right, so I'm going to take the first password from that chain. I'm going to hash it, reduce that, hash that. And I'm going to find that when I arrive at D2, I now know what the password was that produced that. And that's how you reverse with rainbow tables. That's basically how the algorithm works. It's kind of nice and elegant. Right? So one of the downsides of rainbow tables is that it's very hard to construct reduction functions that ensure that you cover the entire password space. So when you pre-compute these tables, you want to make sure you cover as much of the space as possible so that when you do try to attempt a reversal, you're guaranteeing you're looking within the space that you want. Let me kind of go back here. Here on the list for sale, they actually list the success rate. And another way of interpreting that is the password space that table covers. So they don't cover 100% of the password space. You see some here say 96.8%. That meant the reduction functions that they're using were not able to map into those sort of weird parts of the password space. Okay, let me through here. And worst case, if you saw my little trivial example, I started with a digest that wasn't in any of the chains, so I had to do some computation on that digest to eventually find one. There's the chance that I could do that forever and never end up with something that matched one of the chains. Sad face, but that's just the way it goes. There's a lot of also discussion and difficulty around how long should a chain be, so that I can balance storage versus compute time when I'm trying to do a reversal. It's not always clear what the optimal solution is. Excuse me. And there's some other problems. So if I craft a reduction function that produces a password that's somewhere prior in the chain, I produce a loop. And that means I can basically just circle around in the same chain forever. And that's not very desirable. It's not something we want to do. Or I could have 2 chains that at some point merge into one another. That's also a problem. So actually modern rainbow table implementations actually use a sequence of reduction functions. Which again, producing one is difficult, producing multiple is even more difficult, but it will use that sequence of reduction functions in a specific order. So, and that order is known so that when you go to do the reversal, it's pretty easy to figure that out. All right, so based on some research we did at Noblesse, we came up with a new idea. I'm not saying this is better or worse, it's just a different approach. But the idea is, again, how do we shrink the password space, or how do we not visit parts of the password space that we know for certain are not going to contain a successful reversal? All right, so say I want to search through a password space, and then eventually I'll find their little green bar, that's the password I'm looking for. How do I ignore the rest of the space, that white space that I don't want to deal with? Okay. So just kind of a little bit of an explanation and background on this. Let's say I have a password space that is just 2-digit pins, very, very trivial password space. And I have a digest space that are 3-digit alphas. Again, a very, very trivial and simple digest space. All right, so what a hash function does, it will take some set of passwords and map them over to the digest space, and there's no particular ordering, about how those end up. But the problem is, historically this has been the issue, is we've always been trying to track this specifically, the specific mapping between a password and digest. And what we thought maybe would be a different idea is, instead of tracking this, these specific mappings, what if we track regions of mappings? So in this idea, what if we segment the password space into equal size segments? You see on the left, I had 0 to 99 before. I can't actually fit all the segments on the slide, but now I have 0 to 10, 11 to 20, 21 to 30, and so on and so forth. And then the digest space, again, I don't know where the passwords from that segment are going to end up, so I have to map it to the entire digest space for each segment. Okay, this is just sort of just a little background on how we came up with the idea. Okay. So just I'm going to kind of dig into this a little bit. So I have a region, a password region, 0 to 10. And I have a digest space, it's the entire digest space. So for those 10 passwords, if I hash those, I end up with the red bars, which are going to be the specific hashes or specific digests in that digest space. So you can see ABG, BHI, BTZ, and so on. So just keep that in mind. And what this means is that if I want to do a reversal, theoretically, if I'm given some digest, say BTZ, I know that BTZ is within the region or the segment of 00 to 10, because BTZ is one of the digests that I have in that map digest space. And let's say I'm given some other digest, CHP, I know it's not in the space 00 to 10 because it's not one of the present digests. So I can use this information to try to figure out how I can search the password space. So for example, CHP, since I know it's not in 00 to 10, I don't bother trying to brute force that small space to create a reversal. It just saves myself some time. All right, just a few more definitions for this approach. So let's say I have we talked about the password space. A segment then is just a non-overlapping contiguous region of that password space, and we like the segments to be equal sized. The digest space we've talked about, but a digest set is the specific set of digests that are produced under some password space. Okay. A little bit more. So again, just kind of this is a reiteration of what we've talked about. So let's say I have 10 equally partitioned segments. We'll call them P sub A, P sub B, P sub C, and those are segments of the password space. And I have equivalent digests or digest sets, D sub A, D sub B, and so on. This implies that a password in P sub A is in D sub A, right? Or a digest is. And if I want to simulate the reversal of some digests in the password space, all I need to do is see if D is an element of, I have a little example here, D is an element of a digest set D sub A, and if it is, that implies that P is in the password segment P sub A, right? So here's just a quick little, again, some more examples. So given the same digest set we were talking about before, and I have some of it listed up here, BTZ is an element of D sub A, therefore the password that produces that digest must be in the segment P sub A. And DHI is not an element of the digest set D of A, therefore P is not an element of the password space P sub A. Okay. So what does this mean? What this means is that if we segment the space this way, we only need to store the first and last passwords for some segment. So that's a nice little cost savings. That makes it a little bit similar to a rainbow table, but we still need to store all the digests somewhere, right? So it's a little bit bigger than a rainbow table. But we can guarantee coverage of the entire password space. So we're covering the whole space. We can guarantee that. We also, just like a rainbow table, we have to pre-compute all this stuff and then store it somewhere. But once it's stored, you can see you can sell it online and make money, right? It's great. But it should be much faster to simulate R of D equals P, because we start with a digest that doesn't match one of the chains in the rainbow table. We have to do some work to try to see if we can force a match. In this case, we don't have to do that. So what if we can also efficiently store the digests? Right now, we would have to store all the digests that we produce, but what if we could do this in a smaller way, and also in a way that's very quick to look up? And there's a lot of ideas about that. Yeah. Yeah, we want to optimize. We don't want to do a string search and look through that. We don't want to store all the digests. We don't really, we don't really need all that information. So, we did some searching through different kinds of algorithms for the computer science students. Some of these will look familiar, right? So, we don't want to do a string search through all the digests. We could take all the digests and produce something called a trie or a tree, and that could be very, very fast. But then we have to store that somewhere. So we're still storing all the information. There's lots of different ideas about how to do this. What we finally hit upon was some really groovy technology produced in the 70s by a guy named Burton Howard Bloom, and now you know why it's called the Bloom reverse. Not named after the school, unfortunately. But this paper that we're most interested in was called Space-Time Trade-Offs and Hash Coding with Allowable Errors. And it was published in ACM in July of 1970. And the particular problem he was trying to solve back then was that disks, unlike today, were very, very expensive and they were very, very slow. So if you wanted to do like a database lookup to see is something in a database, you didn't really actually want to go check the disk for that information because it just took so long, and the information may not even be there. So that kind of looks like a set membership test, right? Is the data you want an element of the stuff that's on the disk? And what he came up with was a pretty elegant solution. So let's assume we have a bit array. It doesn't really matter what the length is. Here I'm just using a nice trivial example of 8 bits. Okay, and they're indexed, right? And I want to insert some data, ABC. And in his context, what he would be asserting is that ABC would be stored on disk somewhere. But he now wants to store it in this data structure. So we're going to take several hash functions, and these don't have to be cryptographic hashes. This can be anything, just so long as they have properties of being well distributed and have they have sort of various other qualities. But we want to produce a base 10 digest. So if you saw before, what I had were base 16 digests. We just want to change to different base to base 10, right? So if I have several different hash functions, I go ahead and produce those digests, and I'll just mod them by the length of the bit array, and those produce indexes into that bit array, and those indexes are the bits that I flip. Right? So now you see I have some ones in there, and I'm asserting that that information is now inserted in the bit array. Right? And so I can keep doing this for all of the values that I want to store. All the things I want to assert were on that disk. Right? So let's flip some more bits. Assume we've gone through this process correctly. Right? So how do I actually test this for set membership? How does this work? So I'd like to know, for example, is DEF in my bit array? Is it in my set of values? Okay. So I'm going to just use the same hash functions I used before. I'm going to produce the indexes. I'm going to mod them by the length of the bit array. So I get 0, 7, and 6. And I'm just going to look up the bits that were at those locations. Okay. I'm going to do a bitwise AND of those values. And if the result of that ANDing is a 0, then I can assert that the value was never inserted into the set. And that's guaranteed. Okay, let's do another example. Is ABC an element of the set? And you saw how I went through the process of inserting that before, so we kind of know it's in there, so it better be if I go through this. Okay, we're going to go through the same process. We're going to hash it a few times, mod it, get some indexes, look up the bits, bitwise AND those, and 1 and 1 and 1 is 1. So I can assert that the value is likely in the set. That likely is a key part of how this works. So if you assume over time I insert a number of values, it's possible that those values, after they're hashed and then modded again, I'm going to have some collisions within this bit space. I could get false positives. And that false positive rate is controllable by the length of the bit array and the number of hash functions you use. If you look online, there's some calculators that you can use to determine how long a bit array should be and how many hash functions you should use to achieve a desired false positive rate. But the math isn't very, very hard. Right? But we know the converse is also different, right? So if I get a 0 in any one of the indexes, I know it's not in there because nothing was ever inserted to flip that bit. Right? Right? So this algorithm is called a Bloom filter, named after Burton Howard Bloom. But you guys can claim it's named after here if you want. I won't tell anybody. Right? This is used all over the place. If you've ever, like in Chrome or something, tried to go to a website and immediately comes back and says, hey, this site is probably suspicious or bad, Google actually does that lookup in your browser in a Bloom filter. They've pre-cached a ton of what they know are bad websites in some Bloom filter that's inside of your browser. That way you don't actually have to try to go to that site and potentially be attacked by that site. They're used all over the place in databases. So databases will segment their data into different files. And rather than have to see if the information you want is in all those files, they'll check the Bloom filters first. And once they determine it's likely or possible it's in a given file, they'll actually go and check that file at that point to actually look up the real data. Excuse me. If you use Bloom filters a bit, you can get a feel for how they work. You can actually, you can design a Bloom filter to have a desired false positive rate for a given cardinality of the set you're trying to store in it. If you exceed that cardinality, the false positive rate will increase very rapidly, and there's certain properties of how they work. But the idea is then let's assemble all these pieces, right? So in a Bloom reverse system, there's two phases. One is called construction. So a little bit like with a rainbow table, you have to pre-compute some stuff. And you can kind of see here in this diagram, I start with a password space on the left. I segment it into equal size segments. I hash all the passwords in that segment and produce a digest set. And then I take that set and insert it into a Bloom filter associated with that set. And in the Bloom filter, I just call that filter the name of the first and last password within that set. Pretty easy, right? To do a reverse, I just see if a digest is in any of the Bloom filters, and if it is, I now have a digest set that I know that I want to work with, and I have to just simply, and then I know the corresponding segment of the password space it belongs to, and I just brute force that little tiny segment. And if you remember, since we have a false positive possibility, I may end up with multiple Bloom filters that say, hey, yeah, I have that digest. That's okay, because I'm still eliminating most of the password space. Okay, so I'm going to just do a quick example. I'm going to run an example. It's the same problem, right? All nines is the pin. I have a digest. There's the digest up there. This is SHA-512. It's reversing it. We saw it took about 90 seconds before. Now we're done. 6 seconds. Single-threaded on a CPU. Did the same problem. The Bloom filters that make this up are about 800 megabytes, and this is with a false positive rate of 5%. So if I increase the false positive rate, the amount of storage I need shrinks, but the amount of computation I need to do the reverse increases. Okay. And so getting close to the end here, but this does introduce one new problem. Potentially, I have to search all of those Bloom filters. On a very large password space, I could have millions of Bloom filters that I need to search. So how do I deal with that problem? How do I avoid this? Yeah. You Bloom filter your Bloom filters. There you go. Hey, yo dog, I heard you like Bloom filters and your Bloom filters. So yeah, for the computer science guys, you'll see this looks like a classic big O log n algorithm, right? So a little bit more storage. You can even make the false positive parts of this really, really high, and this will still work. You'll see in this really, really simple example, I search the topmost Bloom filter, then it tells me which one, that I have it or not. I search maybe the second layer, and it tells me sort of which ones may have that digest, and then I search the subset underneath of that, and so on and so forth through all the layers until I find the candidate password spaces I want to reverse. Then I reverse those. The reason this is faster is you can see in this example, I had to visit 1, 2, 3, 4, 5, 6 Bloom filters to figure out what the candidate password spaces were at the bottom layer. Whereas if I did a linear search, I'd have to search 1, 2, 3, 4, 5, 6, 7, 8 Bloom filters. So I've already reduced this. If you can imagine this in a much larger system, this is actually is magnified quite a bit. So if you want to see this in action, get ready. I'm going to do the same thing now. We call this a logarithmic search Bloom filter. Don't blink. Done. Okay, so I reverse the same password in 0.02 seconds. And it's about, the data for this is about, it's less than a gigabyte, right, to do this. Yeah. No. The script won't let me run it again, but I can actually show you. I can actually show you the. No, it ran. It's done. Yeah, see, point at 2. I told you not to blink. I made you promise, right? So you can see here's all these Bloom filters. That's the linear search. If you want to see, I'll get you 1 second. Yeah. If you want to see the logarithmic search, you see there's the topmost layer, and each of those folders is another layer deeper within the structure. Yeah. Yeah. So you can, so if you look at these each of these filters is a couple megabytes, 4 megabytes, right? So you only have to, and actually you don't even have to read the entire filter off a disk. Most operating systems will support something called memory mapping files. So you actually, it will make the file appear as if it's in RAM, and then the caching mechanism or the virtual memory mechanism in the operating system will just load up a page worth of data. So like a few kilobytes. So theoretically for each of these Bloom filters, we may only be looking up 20 kilobytes of data for each filter that we're doing a check. Yeah. In the filter. Yeah, exactly. That's correct. You're basically asking it, hey, filter, do you have this? And it'll say yes. You can't always trust it, but if you construct the system with the knowledge of the cardinality, the set that's in there, you can control for what that false positive rate is. Yeah, it says yes, but it's wrong. Yeah, and the cost for that is, in this case, it gives you a little bit of the password space that you brute force, and it's actually not in there, and you just move on from there, right? We don't get sad about it. We just try something else, right? All right. So you saw how it performs. We've actually done a bunch of testing on this. One of the cool things about this is that this is an asymmetric algorithm. So the construction side of this is very, very difficult and expensive. So you can use some expensive equipment, do it once, and save off the results. But the reversal is very, very cheap. So you'll see here's some different examples. Let me kind of skip through here and kind of show you some of the systems we've tested this on. So like a PC running an SSD, reverse construction took 188 seconds. And this is on a password space of just 10 to the 7 passwords. With different false positive rates, but the best times we were getting a reversal was 0.2 of a second. On we have at Noblis we have some supercomputers and some compute clusters. It turns out actually they were slower. This is just for single threading because of the file I/O. So again, you have to read data up in. So if the file system or the storage mechanism you're using is slow for random access, it can slow things down. You'll see we actually ran it on a Raspberry Pi 2. It was able to reverse a password in about 2 seconds. That's livable. I can do that, right? So in theory, we could figure out what constructs the fastest, build it on that, save that off, and then we can do reversal on something very, very slow and cheap. So the idea here is, what if we wanted to produce like field kits that could go out to teams or something that wanted to reverse something, or something so that everybody could reverse passwords. We just do it once and give it to everybody. Right? All right, that's it. Yeah. Most of the time it's from law enforcement. So they've gotten a warrant or something and they've seized a server somewhere, and they need to figure out sort of what the passwords are that are on that server. And that's usually part of an investigation. This doesn't always work, right? Because you have to know, because we've pre-canned the password space, and we've pre-canned the hash algorithm that we're reversing. But so if they're using, that server has some kind of, they're salting the space, or they're trying some kind of weird, variation of a hash scheme, then then the system that we built won't work for that. We'll have to try something else. But we can, even if they use a hash function that we're aware of, but maybe they've used a password from outside of our password space, it only costs us 0.2 of a second to figure it out. and then we can go back and brute force something outside of the space. Yeah, so that's the real problem. The defeat for most of these types of systems is to salt the passwords. What salting does, it's basically something that you sort of add maybe to the password before you hash it, and that makes the password space much, 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 much larger. Not saying it's not defeatable. We could, in theory, we could hash for a given password all the possible salts within a certain salt space. But then you end up with, sort of magnifies the storage requirements of the system. Yeah. Mm-hmm. Any other questions? Yeah. So that's a good question, right? So with rainbow tables, again, like if you, say you use very, very short chain links because you want to speed up the compute time, then you end up with a lot of storage. If you use longer chains, you increase the compute time, you reduce the storage of the rainbow table. This is a little bit like that. The thing that sort of controls that here is the false positive rate. So if I set a really, really high false positive rate, the storage requirements get much smaller, but the compute time goes up for the reversal. If I set a small false positive rate, the storage goes up, but the compute time, goes down. One interesting thing is different hash functions produce digests of different length. And so if I have, the example you saw today was SHA-512, but if I use some other, hash function that produces digests that are 4 times as long, the Bloom filters actually don't get any bigger. They're the same size. Bloom filters care about how many things you're inserting into them, not the length of the things. So the storage requirements, it can depend really what sort of what your goals are. I would say in general, they're probably a little bit bigger than rainbow tables, but if we're willing to sacrifice a little bit more compute time, you saw 0.2 of a second, it's not a big deal. Let's say we set a goal of 5 seconds to reverse a password, then I could probably build a system that would be smaller than a rainbow table. Yeah. Oh, so like for Google, yeah. So I don't know the specifics of the scheme that they use, but in general, what happens is, on most systems, when you log in to a system, first off, you should be doing over HTTPS, so it's going to be an encrypted communication anyways. But likely, you won't even be sending your password into clear. You probably hashed it on your side, but you could send it to them. They will then hash your password. A lot of times what systems will do that do use what are called salts, every user will have a different salt, and that will be known on their side. So when they receive your username, they'll look up your salt, attach that to the password that you've sent, hash it then on their side, and then compare the digest against what they've stored. And that's how they do the authentication. Yeah, and actually in the case of Ashley Madison too, over time, they actually changed the hash function that they used. But because they don't store the original password, they didn't really have an easy way to get the original password to rehash it with the new scheme. So they kept track of which users used which hashing scheme. And so that 11 million or so that were reversed were the 11 million that used the simplest hashing scheme. And that was basically how they were reversed. But there's other ones that were hashed with a much more difficult scheme that are not possible to deal with this, to reverse this kind of way. So probably the best password hashing hash function that I'm aware of is called bcrypt. And the reason that one works is because there's it will send your password through rounds through the hashing function over and over again to try to obfuscate that, but the number of rounds can be millions and millions and millions of rounds, and that's called, I think they call it an effort factor when you hash, which means that to reverse something, if you try a password, you have to then do all that computation just to produce the digest to compare. Yeah. No. That's right, yeah. So that increases the password space. That's basically it. So like, just imagine if our passwords were all just 4-digit pins, you could get into anyone's account after 10,000 tries. For a computer, 10,000 is nothing. But they want us to use all this other stuff. And actually, one of the problems that comes along is they don't necessarily understand that's what they're doing with their password rules, and they'll overprescribe rule sets that actually shrink the password space. They'll say like your first letter has to be uppercase, and your third character has to be a special character, right? And those types of things actually shrink the space. It's when they allow you to sort of put anything in any space that you end up with these very, very large password spaces. All right? Yeah. There is, if you look around on GitHub, there's a whole bunch of implementations of Bloom filters. They're actually not very hard to program, but there's a bunch of them. What most of them assume, though, is that you're going to operate on them when they're in RAM. So they build the Bloom filter in RAM, and the operations run in RAM. What we did is we thought, well, what if we have a system that doesn't have enough RAM? Disk space is much cheaper than RAM. Let's come up with a way of writing them out to disk. And those actually are harder to find. I don't think we ever found any that we really liked. And a lot of the ones that we found require you to read the entire filter first into RAM to do the operation. So what we came up with is this idea of memory mapping the file, so we only had to look at certain parts of the file. Not yet. We're corporate things. We'd like to open source it, but that's the whole algorithm. So it's not too hard to do. The code for this is 100 lines long, a couple hundred lines. It's not too hard. Yeah, we got to write a paper first. And there's scary lawyer people we have to talk to figure out how to open source this stuff. But cool. Yeah, that should be exactly what we should do. So yeah, and actually I haven't. This is actually the first time we've talked about this in public. I haven't been allowed to talk about this for about a year because potentially you can consider it as breaking certain hash algorithms. So you saw SHA-512, 0.02 seconds on a 4-year-old laptop, and we broke SHA-512, but it's still in this standard. So there are some sensitivities around it that we had to be careful of. All right. Anybody else? Okay. Thanks.